In our last video, we took Simpletown, which was 100 citizens in a grid laid out in this very particular pattern, and we discussed how we need to use a different kind of programming tool to write a very large 100 by 100 matrix that takes into account the relationships between each of these cells. So just to walk through a little more specifically what was meant by that, I've created a much smaller example here that we'll be using for the remainder of the videos because it's something we can run our code on, see what the effect is, and then check with our intuition because the example is small enough to really be seen. So I've just created a 3 by 3 grid right here with the numbers 1 through 9. And more specifically, we'd like to use something like Python, which is really good at being generalized to larger things and not having to be done by hand, to create a 9 by 9 grid where we put zeros in this entry if the cells are not adjacent and ones in this matrix if the cells are adjacent. So we generally don't consider a cell to be adjacent to itself, which means we'll put zeros in all the way along the diagonal here. And for an entry like 1, the number 1 is adjacent to both 2 and 4. So we would want to put a 1 in the 2 spot, a 1 in the 4 spot, and zeros everywhere else in both the row and the column. However, when we get to something like 2, the 2 cell is adjacent to 1, to 3, and to 5. So we put 1s in the 1, 3, and 5 column with zeros everywhere else. And if we do this process for long enough, we'll find that there are a couple of different cases. As we've seen before when we were doing the numbrics videos, the corners have a particular behavior, and the outside pieces, 2, 4, 6, and 8 here, have a particular behavior. And then there's sort of a middle type of cell, which has its own type of behavior. So what we'll find as we do this process is that there's a pattern as to which cells are related to others, and that pattern depends a little bit on if we're in a corner case, an edge case, or a middle case. Well, Python is just fine for that. Python can deal with case 1, case 2, and case 3 with if, elif, and else statements. And you can see that the code that we have right here that you'll be filling in this week has a feature called dimension. I'm going to make my dimension example 3 for these purposes, but all of the code we'll work with will work. All we'll have to do to make it a larger example is come up here and change the dimension to whatever we might want it to be, and Python will handle that with no problem. So let's start with 3, and then what we'll be doing is we will be creating a grid. We'll have a loop that runs through the rows of the grid that creates the rows, and a loop that creates the entry in each column, and we'll define the up, down, left, and right values for a particular cell. And then all we'll be doing is checking to make sure if each of those values make sense based on if we're a corner piece, an edge piece, or a middle piece. And then we'll be putting 1s and 0s in the appropriate spot. And that's all we'll have to do in order to use Python to create one of these adjacency matrices. And below, I've run some code from my version of this, which has the values filled in, to show this is what the output of the adjacency matrix would look like. And in fact, this is an example of the output from the 4 by 4 case, but the 3 by 3 case we'll be using a little later on. So once Python is able to create this adjacency matrix for us, what we want to do is input that adjacency matrix into Mathematica, because Mathematica is going to have built in naturally all of the tools we need in order to do this walk through our Excel document. So what we'll need to do when we're done creating this adjacency matrix is output it to a CSV file so that Mathematica can open it. So the last thing I've put in this document for you for Python is what we need to export this matrix into a CSV file so that Mathematica can interact with it. And I've done just that. So here in my Mathematica document, I've created this smallgrid.csv from my Python code, and I'm going to import it into Mathematica and store it as what's called trial. So here for trial, I've included the adjacency matrix for that small 3x3 grid, and that adjacency matrix is a 9x9 grid, and I've imported it and stored it as this matrix called trial in Mathematica. And we can just print that right here. And it looks just the way that 9x9 grid would be in my Excel document. So here we've got a 1 in the 2 spot and the 4 spot for the first grid member, a 1 in the 1st, 3rd, and 5th spot for that second grid member, just like we saw initially. And if you need more convincing that what we have is a true representation of that 3x3 grid in Excel, we can of course call the adjacency graph function on our matrix trial and ask Mathematica to display a picture of what it thinks that adjacency matrix looks like. And it gives us a little grid, which is hopeful. And we can have it label the vertices. And you can see here that cell 1 is related to cells 2 and 4. Cell 2 is connected to cells 1, 3, and 5, and so on. And this little example, you can go back and forth between Excel to make sure that the values you're getting are correct. So for example, 8 should be connected to 7, 9, and 5. Let's go take a look. 8 is connected to 7, 9, and 5. So this information has traveled from Excel through Python and is now into Mathematica, where our next video will show you how Mathematica is going to help us with this gerrymandering task.